IBESS, Ecosystems and Ecology 2, Part 1, introduces population biology, the study of a group of organisms of the same species thus capable of interbreeding and living in the same area at the same time. This movie has its focus on the growth of populations in the environment, with particular emphasis on the J and S-shaped growth curves, typical of populations. This movie will examine the nature of exponential growth and the density-dependent factors that result in the S-shaped logistic curve. Now, this is just an introduction to populations. I have an entire unit on populations that covers the syllabus in Topic 2 as well as Topic 8. Here is the entire outline for Ecosystems and Ecology, Topic 2, in the IBESS syllabus. Use this outline to find the movie you need. This movie has its focus here. Here is the relevant IB syllabus statement. Describe and explain the S and J population growth curves. As humans, we tend to favor thinking about humans, especially when we're studying populations. I want to encourage you to be applying all of the population concepts to populations other than humans. Here are definitions of species, population, and community. A population is a group of interbreeding individuals of one species that occupies a given area at a given time. And this is the subject of this movie. Community ecology will be the subject of the next 5 movies, and that is an assemblage of different species that interact within a defined area. Here is the J-shaped growth curve. The curve displays exponential growth. As you can see, the number added to the population increases with each unit of time. The amount being added to the system is proportional to the amount already present. In other words, the bigger the system is, the greater the increase. Exponential growth results from positive feedback. At the risk of being too simplistic, for example, more adults bear more children results in more adults, thus even more adults bearing more children, etc., etc. Positive feedback is when a change in the direction of a system causes a further change in the same direction. Distinguish exponential growth from linear growth. With exponential growth, the number added to the population increases with each unit of time, while with linear growth, the number added is the same, exactly the same, per unit time period. Exponential population growth results from multiplying the size of the population by a factor, a multiplier. Exponential growth always involves a multiplier, and we'll name this multiplier later in the movie. This is an S-shaped growth curve, the logistic curve. Early in the overall time period, the growth is exponential. But at a certain point in time, the rate of growth begins to decline. Listen to my language carefully. The change in the size of the population, the change begins to decline, and at a certain point in time, the size of the population changes very little, if at all, oscillating around carrying capacity, defined here as the maximum number of individuals the environment can support sustainably over time. In this slide, we can see the J-shaped curve and the S-shaped logistic curve. The growth in any population is purely a function of births and immigration balanced against deaths and emigration. The change in the size of the population over time, delta N over delta T, is due to the relative rates of births, deaths, and immigration and emigration. In time period 1, the population grows slightly, thus absolute number of births plus immigration must be greater than the absolute number of deaths plus emigration. In time period 2, the same is true, except the difference between births and deaths is greater than in time period 1. In time periods 3 and 4, we can see that the difference between births and deaths is actually quite small, approaching 0. The population no longer grows. In this slide, I'm focused on describing the nature of exponential growth along the logistic curve, but everything I mention in this slide could be applied to the J-shaped curve. Notice how the population gets larger each year, but more than that, notice how the number of individuals added each year is increasing through this time period. This is exponential growth. The change in the number added each year is increasing each year. And lastly, we will look at the implications of exponential growth in human populations later in this movie and in the population unit later in the course. Maybe this slide will make the exponential growth more clear. I've asked, compare the difference in the population growth rate, which is delta n over delta t, in year 3 to 4 versus year 5 to 6. You can see that the number added to the population in year 3 to 4, which is 1 year, is less than the number added year 5 to 6, also 1 year. The explanation for this difference in delta n over delta t, the population growth rate, is that the size of the population is getting larger, so when a multiplier is applied, the change in the size of the population is greater each year. Remember that the change in the population size is a function of births and deaths and immigration and emigration. That relationship is shown right here. And that delta n over delta t is known as the population growth rate. Pay attention here because the multiplier has another name and you need to be able to keep them straight. Delta n over delta t, change in the size of the population over time, is called the population growth rate. And you can see that the population growth rate is the slope at any one point in the curve. The slope here at time period A is smaller than the slope here at time period B. This is because through this time period, the multiplier is being multiplied by an ever larger base population size. But take a look at time period C. The population growth rate is 0. But the population size is not 0. So something else must be going on to stop the population from growing at time period C. In this slide, we can see the hand indicating that early on in time the growth rate is rapid. But there's a moment in time, an inflection point, where the growth rate begins to slow as the population approaches carrying capacity. And at carrying capacity, growth is negligible. Or you could say the population oscillates around carrying capacity. Now, can you describe the nature of exponential growth? Exponential growth involves a multiplier, a value multiplied by the size of the population, n. The yearly change in the size of the population, delta n over delta t, is a function of both the multiplier and the size of the population. The multiplier is called the natural increase rate, and we'll understand the origin of this value in the population unit later on in this course. But for now, and through the rest of this movie, it's okay for you to understand that the natural increase rate is calculated using birth rates, immigration rates, death rates, and emigration rates. So here I've defined the terms. Change in the size of the population over time is called the population growth rate, and the multiplier is called the natural increase rate. And no longer will I use the term multiplier for natural increase rate. So, in the red portion of this graph, the population growth rate, delta n over delta t, is indicated as rapid because n, the size of the population, is getting bigger with each time period. But here it is indicated that the population growth rate begins to slow. Now that's not because n is getting smaller. That's not happening. The population is continuing to grow here. But if the population growth rate is slowing, that must mean the natural increase rate is getting smaller. Maybe you can see it here as we compare the population growth rate, delta n over delta t, in 3 different years, 4 to 5, 5 to 6, and 7 to 8. The population growth rate, seen as this value for year 4 to 5, is smaller than for year 5 to 6. In other words, the population growth rate increases. This is because n is getting bigger over time through this period. But in years 7 to 8, the population growth rate is small again. That is because the natural increase rate, R, has gotten smaller since the inflection point roughly here. Now you may be wondering about natural increase rate, and as I've mentioned, it is calculated using birth rates and death rates. But I do want to mention that throughout this time period up to the inflection point, where natural increase rate would then begin to decrease, natural increase rate through this period is at a biotic maximum. I will strengthen this idea later in the course. Here is the next relevant IB syllabus statement. Describe the role of density-dependent and independent internal and external factors in the regulation of populations. I will talk about density-dependent and independent factors here. I will speak more about the internal and external factors in the unit on populations ahead. In this slide, you can see the J-shaped and S-shaped growth curves. Hopefully you understand the nature of exponential growth, where the population increases every year due to a factor multiplied by the size of the population, n. However, in the logistic model, as the population increases in size, the multiplier, the natural increase rate, begins to decline, resulting in the S-shaped growth curve. The population reaches a carrying capacity, which is the maximum number of individuals the environment can support sustainably over time. In this example, carrying capacity is 1,000 individuals. One more image to help your understanding. Through this time period, biotic potential is high because resources are effectively unlimited due to the relatively small number of individuals in the population. But at a certain point in time, various factors begin to shrink the natural increase rate so that the population growth rate declines, approaching carrying capacity. At this point in time, the population has reached carrying capacity. Natural increase rate is approximately 0, meaning that births and deaths are approximately equal. The inputs and the outputs are approximately equal. This is equilibrium, resulting from negative feedback processes. The population will oscillate around carrying capacity because any system change in a certain direction will trigger a mechanism in the system to reverse or dampen that change. This is negative feedback. What are the factors involved in negative feedback in the S-shaped logistic curve? These are the density-dependent limiting factors. Early on in the growth of a population, the J and S-shaped curves are 1. But in nature, once a population reaches a certain size, a certain density, the natural increase rate begins to decline because of environmental resistance, as it's called here, and the curve becomes S-shaped. The natural increase rate is at a maximum through the early period of growth, and this is known as the biotic maximum. Early on in time, the natural increase rate is at a biotic maximum. The population is small and resources unlimited. The population grows and then reaches a critical number, a certain density, above which the population can no longer increase at its biotic maximum. As the density of the population increases, environmental resistance reduces the size of the natural increase rate. And environmental resistance could be lack of food, nutrients, lack of water, lack of habitat, predators, disease, parasites, or competitors. So here are the density-dependent factors that operate as negative feedback mechanisms. Food supply, predator number, nutrient availability for plants, light availability for plants, waste buildup, disease, nest sites, or competitors. Now here are the density-independent factors that limit the growth of a population as well. Now these factors limit population growth regardless of the size of the population. Keep that in mind. A hurricane will sweep across a small Caribbean island and reduce population size regardless of how large or small the population might be. So once again, here's the relevant IB syllabus statement. Remember that I will address the internal and external factors as such in the population unit later in this course. Throughout this movie, I've been using models, graphs, showing changes in the size of populations. The models have been generally illustrative of what can happen to populations in nature, and they help us understand the general trends. However, the curves do not show actual data. They have not been quantitative, thus they do not represent what is actually occurring in nature. Be careful. Lastly, throughout this movie, I have implied that populations grow gently toward carrying capacity. I would like to dispel this notion. Once again, we've been looking at models to assist our understanding of J and S-shaped curves. Populations can display a combination of both curves, where exponential growth results in a population size well over the carrying capacity. The population then crashes back down, sometimes settling at carrying capacity, or in other cases, falling well below the original carrying capacity. We see the J-shaped growth here resulting from positive feedback, and the S-shaped curve resulting from negative feedback mechanisms. Here is a graph, an historical model of human population growth in the human species over a long period of time. Notice that at various points in time, the human population has grown and then leveled, grown and then leveled, etc. New technologies such as tool making have allowed the population to grow before reaching a new carrying capacity. Then again, new technologies, the agricultural revolution, pushed the population to a new carrying capacity. And then the industrial revolution, specifically the use of fossil fuels in agriculture, has pushed the human population into a time period of exponential growth that is not over yet. But our models do not know where the next carrying capacity might be. Do we know the carrying capacity of the human population on Earth? Remember that carrying capacity is the number of individuals the environment can support sustainably over time. Is 8 billion the carrying capacity, 9 billion, 10 billion more, or have we already exceeded the Earth's carrying capacity? And we don't know it yet because we've been polluting and the pollution has yet to come back and bite us. We don't know what the human carrying capacity is because humans have the capacity to change carrying capacity. How? Humans have been able to increase NPP using new technologies. Humans can choose to consume a bit less or a bit more resource depending, increasing or possibly decreasing carrying capacity respectively. Knowing carrying capacity for local populations is even more difficult because one population can trade with another. I will return to this concept in the population unit later in this course. In this graph of human population growth, 3 models are provided, each of which predicts a different outcome based on potential values of fertility. The average number of children born to women in a population is known as the total fertility rate. If the TFR is high, the population will grow in this direction. But if the TFR is modest, then maybe the world will reach a carrying capacity of 10 billion. Now notice the phrase here, fertility assumption. The 3 curves are models based on hypothesized data. The 3 curves are quantitative and help us predict future growth, but the data on which the curves rest is hypothetical. And that brings us to the end of IBESS Ecosystems and Ecology 2, Part 1. Remember that populations and the IB syllabus statements related to populations, specifically human populations, will be covered in a full unit later in this course.